Hello everyone, thank you for coming. So today I'll first introduce myself. I'm Sepehr. I'm currently actually just studying mathematics at the University of Sydney, and I'm going to be going through kind of a niche topic in the new world of AI and artificial intelligence and deep learning, and you hear about ChatGPT and everything all around us. And what I'm going to do today is to try and kind of uncover really what's going on behind all these algorithms, because when we hear about it in the news and when we hear about it in everyday world with industry, they're not out there to try and understand how it works. They're just going to pay someone and get them to do it for them. And now what we want to do is see why they work the way they do, and hopefully that will allow us to understand what they're capable of and what they're not capable of. So the first thing I'll try and think about is, well, why would we want to learn the math behind AI? As I say, you could just go and pay someone to do the whole work for you, make your little AI chatbot or whatever you're trying to make, and then you're done for the day. So there's two reasons I would go for this. So the first reason is, well, if you do that, you're never going to really see what's going on behind the AI black box. And this is one of the big things that people talk about. And in fact, if you want to go into something like the medical industry, when they want to use things like artificial intelligence, they actually find it quite hard to adapt it because they can't trust what it's doing, because at the end of the day, you really don't know what it's doing if you don't have any expertise in the area. The other reason I would go for is if you are actually yourself interested in understanding how to create your own algorithm for a particular problem that may be outside of what's currently known in the data science domain. So those are the two reasons I think it's worth actually kind of peeling back the black box, and hopefully I can try and do that a little bit today. So first, I'll answer the question of who I am. So I'm actually, well, Sepehr, as I said, and I'm studying mathematics. In fact, I'm studying my master's this year in pure maths, and I have my heart actually in data science, because in my undergrad I did data science, physics, and math, and my area of interest is really how we can kind of understand machine learning from a foundational level. And I was fortunate enough to work on machine learning over a holiday through the engineering faculty. So I actually went and worked with drones in simulations and was able to construct a few algorithms that actually do live corrections of the drone's path as it might go through wind forces and other kind of external problems it might have, or even intrinsic problems. And with that, I'm also currently planning to take the AWS exam, because that's kind of got the more industry applications of what's going on in machine learning. And so that's two sides of the coin I'm going to try and kind of bring out in this talk for you. So what we're going to do overall is kind of go into kind of three stages. So what we'll do is start with kind of a generic problem, a very overview of how we're going to think about machine learning in a general kind of case for a specific problem. Then we'll start to kind of understand the general framework of what machine learning is doing in all algorithms. And then finally, we'll go into some more abstract and more important theorems that actually explain why machine learning works in your everyday life. So, and then obviously we'll go to conclusions at the end. So let's start off with this. It seems to have glitched itself up on this website, but what I will try and do, I think this was meant to be a bit smaller, but here's a picture of me smiling. So what's the point of this idea? So we know one of the big problems in machine learning that you might have heard of is identifying if this picture is a dog or if it's a cat, right? Very classic problem, and it's one of those problems that might be interesting if you're trying to detect, for example, where an object is in a specific position, like if you're Tesla and you want to drive autonomously and so on. And in general, you can actually think of this as doing one thing. Really, all you're trying to do is fit some function on all possible configurations of an image. So here, what I'll try and go through is something called the face-based problem. This is just a humorous saying, face-based. Yeah. Anyway, so what we can think about is, let's suppose we want to determine whether if I'm smiling or whether if I'm not smiling. So what we can imagine is this could be one particular configuration of your face, and you may go and consider other particular configurations, and you can do that via some perturbation like that. And what does that correspond to in kind of the face space? Well, each pixel in this phase space corresponds to actually being a new picture. And as I was moving and deforming this picture, you can imagine I'm moving around in this phase space, and if I do some more deformations, well, now I move somewhere else in the phase space. So this is a very high-dimensional space, obviously, but let's forget about that. This is just a two-dimensional representation of that. And you can see that as I kind of perturb my face around, it gets very, obviously, deformed, but this is what you should have in your mind when moving around in the phase space. Now, I can also try to, well, now I can't reset it, because it's glitched out on this, but I will reset by refreshing. Okay, so, well, fantastic. Okay, so let me go back. So, if I now try to make myself a little bit sad, like that, well, it's not going to be very easy, then obviously there might come a point in the phase space where if I do this good enough, it's not going to be very hard, it's not going to be very easy, but if I do this a good enough job of perturbing all my facial muscles, eventually I'll get to a point where I'm no longer happy, right? I might be sad, or I might be kind of, different. I might be doing a bit of a smirk or something. And so you can imagine there is some point at which you went from kind of being happy in the state of that configuration space to some point where you're no longer happy, right? So let's imagine we get our little friends, I don't know, some very hard workers to go explore the entirety of the phase space and at each point determine is this person happy or is this person not happy, right? Let's imagine we somehow managed to do that. Of course, this is an infinite amount of work, but you may get something like this. So now, maybe here we have something like a smile region, and then you might have some another region which is where you're not smiling or you're not happy, right? Now, in those two scenarios, what do we have? We have basically a boundary forming in this phase space. So that's the idea you should have in machine learning. So why is that important? Well, machine learning at the end of the day is really just trying to figure out this whole picture. For each picture you give me, like maybe I'm smiling or not smiling, it just needs to tell me, is that smiling or not smiling, right? That's what this yellow region is, and that's what that blue region is. But over here, you may have some sort of ambiguity forming between the two spaces. So maybe if you're around there, you may be definitely happy, like you've got a very big grin, but then if you're at the top, you may very much have a big frown, right? So those regions, there's no ambiguity, but once you start coming towards the center, where now there's ambiguity, because it could be the difference between a smile and a frown kind of coming together, that's where machine learning is doing most of the work, because that's really where the ambiguities are, where the machine has to figure out what to do. And in this case, you get these little pixels overlapping, so you might have some sort of yellow dots over here, where that might correspond to maybe perturbing your face just a little bit somewhere else, and then that might be the difference between smiling and being a grin, or being a smirk, or something that kind of looks like a smile, but it's actually a different emotion, right? And in the other case, you can have these pixels kind of overlapping in the yellow region, and that corresponds to if you're like just doing the opposite, so you're about to start smiling, sorry, about to start, so you start from frown and you're just entering kind of a region of where you're smiling by choosing some new perturbation of your face. Now, this is the picture you should have in your mind as we go around this in machine learning, because that's all we're trying to do. We're trying to come up with a function that fits the space. So one particular function you might say, well, all those little pixels, that is really annoying, right? If you tried, you could try and fit a function that goes around all those individual pixels and picks out everywhere that's a yellow, everywhere that's a blue, but in practice, you might find that this is going to take an infinite amount of work, and you're not going to be able to do this in time for, like, I don't know, getting sales on your next big business trip or something. So what we want to do is try and kind of limit the amount of work we have to do and not do infinite amount of work, maybe do finite work in some sense. And the way we might do this is by constructing some sort of approximation to what this boundary is. So in this case, I may just go and fill out where the majority of the phase space boundary holds, and I ignore the fact that I'm getting all these ambiguities showing up on other end, and this would be a misclassification in this sense. So I would say all these blue pixels correspond to yellow if I choose everything below that black line to be yellow, right? And vice versa in the other sense. So this is kind of a simplification because now we have less work to do, but of course in practice this is still difficult. And so one other thing you may want to try and look at is if you aren't certain how to deal with those pixels, is you might construct a new way of thinking about these logics. So before we were thinking about it's definitely smiling or it's definitely not smiling. But in reality, especially if my face is kind of doing a lot of random things, like about to smile or not, for a human like yourself, you're going to find it also hard to actually say deterministically whether if that's a yes or a no to smiling. And the same thing is true for a machine, and that's how we should try and kind of think about it. In the case of fuzzy logic, this corresponds to kind of blending the two regions together, and that means our logic values are really an entire continuum between 0 and 1. And if you want to kind of think of this as a particular algorithm, this would be something like logistic regression, if anyone's heard of this. So that's where now you, instead of saying yes or no, you kind of allow a continuum of logic values in that sense. Of course, if you're a doctor, let's say, and you're trying to say, yes, that person has this disease versus they don't, you still have to do some sort of definitive change at some point. So how do we deal with that? This hasn't really fixed the problem, it's just sort of allowed new logic values. Well, one particular way you might go about this is using something called a confusion matrix. So I'm not going to go into the details of how that works, but if you ever do anything in data science, this shows up a few times, where you might use these ideas of confusion matrices or ROCs. These are very technical things, but all they're really trying to do is figure out how much we're going wrong at the boundary, like how much of the overlap is going off where we didn't want it to go. So if you're a doctor, let's say, you may really want to figure out every single time where someone is not smiling. So that corresponds to moving your boundary around so that you really capture every single non-smiling region, right? That might be the case when, let's say, you're a bank and you're trying to figure out fraud, and maybe you want to detect every single fraudulent transition at the expense of maybe also kind of misidentifying some normal people as being a fraudulent transaction just in this case. And that's why you might be interested in doing this. And of course, you may also do the opposite scenario as well. So this is the picture you should have in your mind. Machine learning really is about fitting functions, and it's also about changing our functions around until we're happy with the results we have. And it really models what we want it to do in our everyday perception of what the machine should tell us. Okay? So now let's kind of try and level up a little bit. So we now know machine learning is doing some sort of function fitting on spaces. And I'll try and give some sort of new way of thinking about it. This is, of course, really abstract. Don't worry about this. I'll give some examples in a second. So what we might think is before we have some function, right? And this here is some function on our space, like it's giving out a yellow and a blue and so on. And then you might want to think of this as a continuous function. And that's really just so you can reduce the amount of work you have to do. If you want to choose arbitrary functions, that's got way more work you have to do in the process compared to just using continuous functions. So what we'll do is restrict our AI models just to continuous functions. And here, I've got x and y corresponding to maybe the space of all faces, all the ways I can turn my face, and y would in this case correspond to, am I smiling or not? Okay? And you want all continuous functions between those two, and what your AI model is doing is saying, I want to kind of have a countable, finite representation of my continuous space, so I want to be able to move around there without having to do infinite amount of work. So I'll show what that looks like. An example is using something like linear regression. This is a very simplified example, and you've seen this probably in high school. So an example of that is you have your model space giving you back a continuous function, which is a linear function, and here you use parameters, A and B, for example, to allow you to move around in that function space. So I'll show you what that looks like. So again, this has screwed up this pixelation. Anyway, so what I've got here is my model, and I can move around by just changing these parameters. So each one of these green lines is another linear function, and what I'm doing is moving moving around in like a continuous function space. And now, this is obviously very simple, and linear regression you know how to do a lot from high school, but you might want to do something a bit more complex. For example, quadratic regression, or just a model, like a quadratic model, and now you can imagine moving around in this space corresponds to finding a new parabola. But this space is actually kind of a bigger space than the linear ones because you can set these to 0. And now you get back to a linear function by just making this last one 0. So these are very simple examples, and hopefully that gives you an understanding, because now we're going to ramp up to the next level, which is neural networks. Okay, so what is a neural network? Well, we know neural networks are something you hear about all the time, they're just random things. Really, they're just a bunch of continuous functions at the end of the day. And what you're doing is you're starting with some parameters. So in this case, I've got 7 parameters that I want to be able to move around in my space with. And then what I do is I do some specific mapping that takes some affine combinations. So you've got matrices, you've got inner products happening, multiplication like dot products, and then you've also got something like a nonlinear function in the process. So in the case of neural networks, these nonlinear functions are really exactly what allows things to work. Because if this were a linear function, a neural network at the end would just be a composition of matrices, and that, if you haven't done matrices yet, that'll just be like a bunch of linear equations, and that will just give you back this simple space, right? And if we go back to this simple space, well, if our data was doing something very, very funny, then, well, that's all we're able to access. We can't access anything else in that space. So we're going to introduce this nonlinear function called a ReLU. This is a very common one used. There's other ones out there. There's like sigmoid, there's hyperbolic tangent, and they all actually have to satisfy some sort of property in order for the neural network to work in the way we want it to. So, excellent, it says. Going off to the side. Okay, let me try bring this to the. Yes, this whole website has glitched out of this new pixel. Okay, so what this is supposed to be is a one-layer neural network, and what I'm going to show you is because of its nonlinear function, it's able to actually kind of approximate any nonlinear function you give it. Maybe here just from the real line to the real line. So let's say I've got something like sine x, that's this red curve, and then the neural network automatically tries to kind of find a function that best approximates that nonlinear function. And I might do something a bit more funny, like let's do a parabola, x squared minus 5, and now the neural network will try its best to fit that function. Now here, it's obviously not doing that good of a job because you can see it's missing a lot of this area. And it turns out, if you want this to get better and better, you can always do that just by adding more nodes in your hidden layer for a neural network. And we will go through a theorem that will allow us to understand why that is. So that's kind of an example of how these model spaces are working. You're really just spitting out a continuous function for every parameter you give it. And one thing you may be interested in now is kind of understanding how badly your model is doing compared to the real world and what you expect there to be in the real world. So what we'll do is come up with something called a loss function. And the loss function at the end of the day is just measuring how badly our model is doing compared to what it should be getting out there. So if I've got the function I really want, my true function, and then I've got this model, right, that's kind of not hitting all functions, it's only hitting continuous ones, and even then I'm only hitting finite space of continuous functions. So I need to be able to measure how bad I'm doing, and that can be done through something called a metric. And I'll just assume if you don't know what that is, don't worry about it. I'll give it an explicit example. One simple example is maybe doing an integral of the squared differences between your function and the model. So here, I've got that sine x again, and maybe I've got a linear model, and as I move around in my parameter space, the area between those two curves will give me a kind of a measure of how bad my model is doing. And it turns out there exists, in the case of the sine x, there exists some point where you actually get exactly a minimum. And so that's what I've implemented there in Desmos. So we'll go into understanding how that works, but what it's really doing is trying to optimize these parameters such that you get a minimum in your loss surface. So you can imagine at each point as I move around, this loss function has a new value, maybe 5, and I move around, has another value, and then we want to get that loss value to as small as possible, which kind of says, yes, we are as close as possible to the true function we're trying to approximate. So let's try and understand how that works in practice. How do we actually get these loss functions and minima to show up? So this is the sine x curve before, but this is the loss surface of that sine x graph. So here you can imagine it's this parameter space, and what I've done is I've shifted it up where the where the z value is now just the value of that loss function. And that's this loss surface. Okay? And what we're trying to do is find the minima of this surface, which you know how to do from calculus perhaps. This just corresponds to moving your way down to this minima point. And you can do this very precisely in higher dimensions if you have access to something else, if you have access to something called an optimal parameter search algorithm. So this, at the end, is just what we're doing before. All I want to do is just go to the minima of my loss surface, and so I've really found an optimal function in the model space. Now, in technicality, this is not necessarily unique. There may be multiple minima out there, and this might be because the goal function you're trying to get may be overcovered. So let's see how that makes sense. If I go back to the parameter space and maybe make my model space be kind of cosine AX plus B, now, as I move around, my model space is all continuous trigonometric functions. And you can imagine as I move around my parameter space, I'm trying to kind of fit it. But there are a bunch of minima that show up here. So if I run this minimization, well, there's a minima there, but that's not necessarily the best minima because it's sort of done its best in the place it's at. So this actually is a loss surface with many, many valleys and hills and so on. So let's see what that would look like if we kind of go a bit more crazy. Let's say we want a very weird valley surface where you've got many, many valleys, right? We just want to get to one value just for now. Then we'll discuss whether if that value we went to was a good one or not. So here I've got a surface, loss surface with many, many valleys and hills. And the way I want to move around in this space is such that I get towards my minima. And the algorithm that a lot of people use in machine learning at least is called gradient descent. So if you know any calculus, this is the gradient that you might be familiar with from calculus, the same gradient that you compute, the little nabla symbol, and that's exactly what I will show here by bringing this. So this is actually computing the gradient live, and if I move around, whoops, let me go back up. So as I move around in my loss space, the gradient is going to be that vector A, and that vector, the gradient, will be the one that points towards the greatest ascent. It points towards which way I should go to go up. If you take a minus of that, it points towards the direction of the greatest descent. And that's what we want. We want to get to that minima of that lost surface. And so that's what this does. This points towards the minima. So what I'll do is, if I'm kind of somewhere in this function loss space, I just want to move towards the minima. So I just follow the direction of that arrow. And then hopefully I'll get to the point I want. So that's exactly what the gradient descent algorithm is. So here you compute exactly the gradient, the same gradient from calculus. Then you maybe want to start with your parameter at some point, and then move your way around in that space. And that minus is there because the gradient needs to point in the greatest descent area when we go to a minima. And then you have something called a learning rate showing up here. So this is something that shows up everywhere in machine learning. A lot of neural networks have something called learning rates. And these are basically just telling the algorithm how big of a step do you want to make every time you try and find the minimum, right? And if you make very big steps, well, that might get you far pretty quickly. So if I make a massive step, when I'm over here, so let's say I'm over there, I make a very massive step, I might jump to this point, and yes, that probably got me pretty close. But if you have a valley and you're near the top, right? And then you make a massive step. Now you're going to fall onto another top hill, and maybe you might just start jumping back and forth between these, and you would never actually reach the global minima, or even a local one. You might just get stuck. So that learning rate you really have to optimize, and there's no way around it. So this is why you might see something called hyperparameter optimization in machine learning. But if you choose a very small learning rate, what's going to happen is you might move forward a little bit, and then a little bit, but then the gradient, because we're approaching a minima, the gradient is getting smaller and smaller. So you might get to a point where you never make any moves at all in terms of the small gradients you're getting. So you might get stuck here, and then it's going to basically take your algorithm until like next month to finish converging. So that's something you have to be aware of when you do these. Okay? And what we want to have is the gradient descent algorithm. We know that it goes to local minima, but we really need to justify that this is good enough. And there's a theorem that will allow us to do that, and we'll go into that soon. So hopefully this gives you an idea of one possible optimal parameter search algorithm. Now let's go back to what I was showing. So this gradient descent, as you see, what I was really doing is computing the gradient of that loss function, and that's exactly how I was doing this optimization in this loss surface. So I run that algorithm, and there it goes, just computing the gradient over and over and over, and then finding its way towards that minima. Okay. So now that's kind of the beginning of this thing, of loss surfaces, loss functions. Now let's talk about in practice how we actually do this, because obviously right now these are abstract functions and we don't even know what the real function is at this point, right? Well, that's where you need to start coming into kind of talking about statistics. So statistics is really kind of understanding how you turn this abstract function stuff into tangible computation tasks. So before, you remember I had that loss function, which was that random integral looking thing. It turns out this has, the reason we use this loss function is because it has a lot of nice statistical properties, but also a lot of nice mathematical properties that, for example, introduce things like measure theory and so on. If you don't know that, don't worry about it, but this is quite important in machine learning for this way. So let's go on to this. So what happens if we have finitely many samples we've taken of our space? Like, I only have access to finitely many pictures of my face. I'm not going to wait an infinite amount of time for that. So what I want to do is approximate my loss function, which was an integral before, but if you know anything about Riemannian integration, you know that if you have a convergent integral, you can approximate it by some sort of sum. And in this case, this sum is over all the data points you've taken. And if you have more and more data points, this should, in theory, assuming you've got randomly distributed, uniform sampling and so on, you really will have this converge to the true loss function, and that should hopefully give you the minimum of where you want to be. And remember that we don't actually know what f of x is in practice. All we have access to is the outputs. We only have access to the y's, which is just what the sampling of our data is. So up there, I've got points xi, yi in our space, and we only have access to that. We don't know what the whole function is. And hopefully the model is what brings us access to some close enough approximation of that true function. Okay? So now let's go on to, so now that we've kind of got a generalized picture of machine learning, let's now try and justify rigorously or mathematically at least why we expect things to work and why we don't suddenly end up going randomly diagnosing everyone to have cancer or something, or really random, nothing, like nonsense going on all over the place. So the first reason why machine learning in particular works is something called the Kolmogorov-Arnold representation theorem. So colloquially, what this is saying is that the only multivariable function, so you might have some very, very multivariable, like big space, Rn, and it might be a very big, well, it's obviously, we have to remember when it's focusing on continuous functions. If you've got this function that might be very crazy, it turns out you only really need to write it as a sum of single variable functions. And that's really because in the case of continuous functions, the epsilon delta definition really restricts the type of functions that are allowed to be out there, and that's why we get this. This is one of the Hilbert problems that was famously solved, and this gives us access to really working with single variable functions all the way through. So this is where we get something like feature engineering. So this, if you don't know what this is, a lot of techniques in machine learning rely on you individually doing transformations to your data. Maybe you have one dimension of data and another dimension of data. You might individually transform those and then combine them in some sort of sum. And that's why we're allowed to do this, because of that representation theorem. And now, the next thing we'll go into, this is really the crux of the neural network. Why does the neural network give us any reasonable model? It's because of this theorem here, the universal approximation theorem. So what does this say? Well, before, you remember I had a neural network and it was kind of trying its best to approximate that random nonlinear function I gave it, right? That function, it looked like some very horrifying matrix multiplication and a ReLU, but in its essence, it's actually quite a simple algorithm compared to a lot of algorithms out there. So all it's really doing is taking your data x, multiplying it by some matrix, this is a matrix here, adding it to some other vector, and then computing now that nonlinear function. So this sigma may represent the ReLU, which is what I had before, but it also may be other nonlinear functions, for example, maybe the hyperbolic tangents and so on. So what are the conditions on this algorithm, or this whole thing to work? We need that sigma actually be non-polynomial. This is, again, because of complicated reasons in mathematics. It turns out that if you have a polynomial one, it's going to shoot off to infinity too much, so you actually will have a hard time piecing it together to form your function. So I'll try and give an example, and one other thing I'll say about this is, in this case, you can actually take your loss function to just be the biggest possible value between your two functions. And so this is quite a very strong approximation. It's saying you can basically get the functions to overlap almost eye to eye in this sense. Right, so now let's go on to, again, this is glitched out because of the resolution of this computer. Now, I've got there the same neural network before that you might have seen, right? And I could do something like bit x squared minus 5 or a sine x curve, and that's what was doing that. Now, I told you before that you can make arbitrarily precise approximations to nonlinear functions using neural networks. And if that's the case, I should expect that if I ramp up this to the next level, maybe instead of having 2 nodes in this hidden layer, I may want to ramp that up to the next level. So maybe let's do a 3-layer, a 1 layer with 3 nodes in the middle, and there you can see that sine x now has been fit way better just by adding another node in my neural network. So in essence, what's going on is you're piecing together your sigma maybe was your ReLU function, which is some nonlinear function. You piece these together, and if you have enough nodes, you have access to more of them, so you can actually do more movement around in your function space, and that's how you can actually get hold of any of these nonlinear functions. So let's try and see this a bit more precisely. This is the ReLU function I was talking about. So it basically is nonlinear, even though it looks like it for a second, because once you go above x, it's linear, but before here it's flat, so it's linear if you just restrict to those domains, but overall it's non-linear because you basically can't write it as a sum. You can't add them together and get another ReLU and so on. So you have to so you will get non-linear things in this behavior. Now what the ReLU was able to do, or any sigma you chose, non-polynomial, what it's actually doing is approximating something called the ramp function. And this is basically 2 ReLUs put together. You can think of it like, you can get that ReLU and another one, flip it, and put it together. And what the neural network is doing is getting these ramp functions, just copying them multiple times, and that copying is happening when I add more nodes. It copies, pastes them, and then what it does is it just places them around my function, my nonlinear function. And no matter how hardcore your nonlinear function is, if you just add more nodes, you can get them to kind of do their best of getting those ramp functions to fit that nonlinear function you were interested in. So that's really why neural networks work the way we want them. And it's really because of this universal approximation theorem. So, of course, in practice, you may not necessarily use ReLU, because in practice we're having to deal with finite calculations. For example, we're calculating things like derivatives in the gradient descent algorithm. So you may use something that has a bit of a kink at the bottom here, just so your gradients don't vanish to zero and you don't end up getting stuck in your lost surface. But that's more technical, so I won't really go into that. Now, this is where we start stepping up again into what machine learning is doing. One of the big problems we saw before is we may have a surface with many global minima. Many local minima, right? You may get stuck somewhere in a local minima. And the question you may ask is, well, should we be done? Should we try more? Because remember, we don't know what the entire lost surface is. We may be stuck for the next month trying to figure out where that minima is. So what we might have to think about is, how do we know when we are good enough, when we're close enough to the global minima? So it turns out for these large neural networks, any local minima with sufficient assumptions, there are a lot of assumptions going into this theory, will actually be able to be close enough to the global minima. Any global minima. A global minima will be very close to all these local minima. Okay. And this is thanks to something called the spin Hamiltonian loss correspondence. So what is that? Let's take a little crash course in Hamiltonians. So these things are from physics, and what they're doing, so remember, this is two different things. We're talking about machine learning. Now I'm taking a big leap off to physics for a second, because it turns out these two areas are trying to solve similar problems, and this is where you get a correspondence. So it turns out if you take something like a Hamiltonian of a particle maybe in gravity, what it's doing is quantifying how much energy that particle has, and what this kind of quantifies is how much the particle is willing to transfer its energy around the place. And so if you get to a local minima in your Hamiltonian, that corresponds to the particle kind of being happy where it is. It doesn't really want to move around anymore. So you can start thinking back to what we're doing in loss functions. If I get to a point where I'm happy and I don't need to move around anymore, there is, you can see some sort of correspondence going on in this case. So let's go on to now what we can do with these Hamiltonians. So as I said before, when we have energy moving around the least, that just corresponds to being kind of at a minimum of a Hamiltonian. Okay. So now what is a spin glass? So this is something else again from physics. So this is something that physicists have been interested in, and this is something in magnets. So one of the questions you might ask is, how does a magnet work? How does it allow things to actually attract to each other and so on? And the way they model a big block magnet is being made up of tiny little magnets, which are really just tiny particles that have something called spin, and that's what that spin glass is. And in the case of spin glass, you allow these particles to have any orientation in three-dimensional space. Now, if you go and take these and write down the Hamiltonian, it's a horrible thing. Don't worry about this. This is just what it looks like. The spin glass Hamiltonian is this very, very massive formula. And in the case of spin Hamiltonians, it turns out that in random matrix theory, which is actually where this theorem comes from, they're quite interested in n-dimensional magnets for some reason, so here you get n-dimensional things. You also have things like the number of neighbors you might consider. So one of the things with these spin glass Hamiltonians is they're actually little magnets will actually pull on each other locally if they're next to each other. So they actually influence each other, so you get kind of movements around. And so you might consider more and more neighbors that would actually give you access to more information in that sense. So you get the spin glass Hamiltonian, and here's the big theorem that was proven using random matrix theory by Affenguy and so on. And what they showed is that if you get some minimum of this Hamiltonian, it turns out that this actually will be very close to the global minimum. And I'm not being precise here. They're actually using a lot of assumptions and a lot of epsilon delta definitions of being close and so on, but just think of it as they're very close to the global minimum. So this is good. We know spin glass has this property where if you're close to the global, if you're close to the local minima, you're close to the global minima. But now let's try and map this over to a loss function from a neural network. And it turns out, this was done by Koromanska in 2015, and it turns out that you can actually make a correspondence between your lowest energy state in a spin glass Hamiltonian and your local minima as a loss function of a neural network. And this correspondence means that you actually know that if you have some sort of local minima in your neural network with a bunch of assumptions, then you have a local, and you indeed are close enough to the global minima itself. And that's really why in practice, when you train your neural networks, you can be happy that in a month or whatever time it takes, you're not going to be burning your money out the drain because you just spent a month doing nothing and getting no good results. So you really will get pretty close with obviously reasonable assumptions in there. Now, this actually kind of explains, as you see, you get these spin glass movements to lost surfaces. So this is not really saying anything new. Okay, so now let's move on to another topic which is very big in machine learning. So we're now ramping it up again into abstraction land. So this is something that a lot of machine learning has to focus on because, again, we're dealing with finite data. And in practice, you don't have an infinite amount of time to go do infinite amount of sampling. You only have access to finitely many things. And so you really don't want your model, when you've only got finitely many data, you don't want your model to really hit on those data points and call that a day. Because if you overfit on those data points, well, you may have not sampled enough. And so when a new data point comes in, you may be kind of out of the box completely when it came to what the first few data points were doing. So what we want to do is force our model to not be super focused on getting those data points right. So you don't want to have a line go through every single data point. You kind of want to make it smooth out a little bit, so generalize it a little bit, and that's by something called regularization. So if you want to have something called this hyperparameter lambda, this is something you just choose, and this basically biases the model in such a way so that it forces your numbers in your parameter search to be quite small. So this thing here is, again, another integral thing, and what it's saying is I don't want this thing to be big. I want this to be small, which is also saying I want my model as close as, I want my model to kind of force itself to have big data points arbitrarily. I want it to be very, very constrained and very smooth in a sense. So it's doing a lot of work there. And what it turns out with the representative theorem is this thing here, in practice, is going to be quite annoying to get a hold of, this loss function, and of course, getting a hold of the best model that we should choose. It turns out that this representative theorem uses something called a Hilbert space. So, if you don't know what this is, I'll just give you a quick intro. So, before I was talking about this space called L2. And it turns out this is something called a Hilbert space. And if you think about angles in maybe linear algebra, they give you two vectors. You can get the angle between them just by thinking of a dot product. It turns out you can kind of construct a dot product for spaces of functions. So in two functions, you can think of the angle between them in this abstract sense. And this is through this inner product, or a dot product, really, if you think of it. And it turns out that by using this inner product, you can actually really simplify your problem down before and get a model that is very much just a linear function. And I'll say what I mean by that. So it's very linear and it's very fast to approximate. So I'll show you how that works. So the trick we're going to use, maybe I'll just show a picture first. The trick we're going to use is, let's say our data is right now it's quite non-linear in the sense that I've got these data points, and maybe I've classified these ones to be purple, and I've classified these ones to be red. If they're on a one-dimensional line like this, that's going to be quite hard to put a function around it. You have to do some work to get that to happen. The trick with these kernel things, and these Hilbert space things, is you find a high enough dimensional space, which is also a Hilbert space, such that when you take your data into that space, now you get a separation in your data points in a new way where now you have access to inner products, so angles, and by using those things, those angles, you can actually differentiate where a lot of the data is close by. So here, you've got some pretty small angles, and here you've got some bigger angles, and that's where you can now start to differentiate your data in an easier way. And this becomes a linear differentiation compared to before where you had to really have worked really hard to oops, I put that up. You really have to work hard to get a good function that fits this. And so let's go into how you do that. So that's by basically, this is all technical stuff, but really you just want some sort of inner product or angle measurement. You want to take your data points to some high dimensional Hilbert space, construct something called a kernel. So this kernel is not just an abstract thing from this case. This is actually the same thing used in convolutional neural networks. This is the same thing used in Fourier analysis, which is how you do signal processing. And this is now, of course, being used in machine learning. So if you do this sort of thing and measure these angles, then you can do what I said. And it turns out, if you have your finite kind of data representation of your integral, you get a very beautiful linear function. So I'll show you what that looks like if you've got access to that kernel. It turns out that you now can just write it as a sum of some points times your kernel function. So this is predefined. And now you just get a nice linear function. And so this is very fast to do approximations and do quick fitting in live scenarios. So I actually looked into this a lot when I was doing my research over the holidays. So as you saw before, I was working with drones and things, and it turns out in the context of reinforcement learning, which is another big layer of machine learning, where you now consider your state space to be some infinite dimensional space, and you've got your actions, which is you've got a robot here, and now it wants to move this way. I need to tell it what to do at this point in time, and that's a very high dimensional space, and I've only got access to finitely many sample data. So having access to that linear representation by the representative theorem, it turns out that this becomes a much easier problem. And so that's why this actually shows up in practice, because now you can actually do this similarity measure and get very efficient calculations going on, efficient models. Okay, so that's the big conclusions. Overall, you really see that AI, it's not some magic, it's really secretly the study of functions. And then we saw that the Kolmogorov-Arnold representation theorem is why we have these feature engineering things just being able to be added together. And then finally, we've got neural networks and how they're very successful with approximating continuous functions. And the spin-class Hamiltonian correspondence tells us that if you get a local minima, you're pretty good. You don't need to worry that much. You'll be close to a local minima. And then this thing here, the representative theorem, was giving us access to kind of a linear thing, linear representation of our model, and that made it very efficient with approximating things. Okay, that's everything. Thank you. Hope you've enjoyed. Any questions?